Okay, welcome back everybody. I hope you had a nice spring break. I did, but it's good to see half of you back. For some reason this half came and this half didn't come. I'm not sure why, but if you like you can move over here and I'll just talk to this side of the room. Here they come, here they come. They're still on spring break, I guess. All right, as you remember, we were in the middle of a pretty complicated topic. We were in the middle of how to help our pipelined processor handle control hazards. Right? The data hazards didn't seem so difficult once we got into control hazards. They seemed quite a bit more challenging. And so we looked at jumps. Not too bad because we're always jumping. Then we got to branches and we realized sometimes we branch, sometimes we don't. And the price of the penalty for waiting is too high. So what we tried to do, if you remember, is lower the penalty by moving the branch decision point into the decode stage. And the way that we did that was to be able to compare the two registers in the decode stage, not in the execute stage, but this comparison function has been taken from here and put here. So we're actually fetching the two registers and immediately comparing them to decide if they're equal or not. And of course on a BEQ that means take the branch if they're equal. On a BNE it means take the branch if they're not equal. So we need that information early. Okay, so that reduces our penalty now just to one cycle. We obviously still have a problem. We don't know the answer here, and so we don't know what to fetch in the next instruction fetch stage. So that's what we've come to right now. So this is called, the hardware is in red to support instruction decode stage branches. Remember, fetch, decode and get operands, execute, memory, and then the last one, which is this and this again, write back, our 5-stage pipeline. Okay, so that's where we were. And we realized that not only did we need a forwarding unit here for these muxes to help us solve the data hazards, now we need a forwarding unit here for these muxes as well to solve the control hazard. Because what we need is to get the current value of the two registers, and that means the most recent value, which might be coming from this pipeline register or this pipeline register, back to here. Remember that? Yeah. The data here isn't guaranteed to be the latest. It could be. It's right here. We just changed the register value, but it's not back here yet, so you have to forward it to bring it. Okay. And then in addition to that, we're going to have a hazard unit. Sometimes we're going to have to put zeros in all my control values in order to flush the pipeline, etc., etc. We remember all that? I know it's been 10 days, 12 days, but I want us to remember what are those red structures and what is their purpose in controlling the extra hazards brought in by pipelining. And you may say, Hoja, what is all this complication? Isn't it just so simple to, execute an instruction? You fetch it, you decode it, you execute it, you figure out if you have to write into memory or read from memory, and then you put the results back. And the answer is yes. It's very simple if you don't pipeline it. But when you pipeline it, remember we promised you, we said pipeline is cool, but it brings some very interesting challenges. We're working on trying to solve those interesting challenges. That's where we are. Pipelining is great, performance is wonderful, but you got to fix some problems or you lose a lot of your performance. Okay, so that's what we're doing. Now, we're going to continue on with approaches to reducing the penalty in control hazards. All right, we're still working on control. They are quite a bit more complicated. You'll just count the slides and count the minutes and you'll realize he's spending a lot more time working on solving the control hazards than we did on solving the data hazards. And that's of course because they are quite a bit more complicated. All right, delayed branches. If the branch hardware has been moved to the instruction decode stage, then there's going to be a stall of one cycle on every single branch unless we start to do some extra things to try to reduce it to less than every single branch, right? That's the idea here. We can eliminate all the stalls with an approach called delayed branch. Wow, never stall. That sounds great. Good, that'd be wonderful. What is delayed branch? Well, the definition of it is given here. We always execute the next sequential instruction after the branch instruction. In other words, the branch will take effect not immediately, but after one more cycle. So we fill that cycle where we don't know what to do with useful work. So instead of drinking tea and wasting it, we put something useful in it, and now the penalty is essentially 0. Cool idea. It depends, of course, on being able to fill that empty cycle always with useful work. Where have we seen that trick before? Fill the empty cycle, don't drink tea, but do some useful work. Where did we see that before? In solving the data hazards. Remember, we talked about one approach would be reordering the code so that loads are not immediately followed by a use of the thing. Remember the load use hazard? Separate them, stick something in the middle. Now you don't have to have a stall on load use hazards, which are unsolvable by forwarding. Remember, we fixed a lot of data hazards, but there's one data hazard we cannot fix. That's the load and then immediately use it hazard, unless you separate them and put a line of code in between to do something different, not with that value, of course, not with that register, but with something else. Same idea here. So if you could always fill it, then you could reduce the penalty to 0. We call this delayed branch. The idea is that you can't know immediately where to branch to. You can only know one later. So the branch is delayed. Let's redeem the time in the middle with something good. All right, so the MIPS compiler now is needed to do this. It's compiler reordering, like we talked about before. The MIPS compiler is needed to move an instruction to immediately after the branch. And the instruction has to be the kind of instruction that's not affected by the branch. In other words, its value doesn't depend upon going or not going somewhere. We call it a safe instruction. And therefore, it hides the branch delay. So we have delayed branches, and we're going to hide it with useful work. That's the idea here. It's a great idea. But the problem is, with deeper pipelines, the delay is not 1. The delay goes up to n delay slots, and now you have to find n instructions to fit into there. We have a little short 5-stage pipeline, which is not too bad. Usually the compiler can find something in many cases to put there. But if you have a 10-stage pipeline, you have to find 4 or 5 or 6 or 7 useful instructions. You're not going to be able to do that most of the time. So we're still going to have penalty. Still going to have wasted time. The compiler is less likely to find n safe instructions than just 1 safe instruction. And as a consequence, delayed branches as an approach to eliminating the hazard of branching and control is less popular than it used to be. And a more expensive technique, but more effective technique, which uses dynamic hardware instead of static software. Let's see if we can unpack those terms a minute. Dynamic means it changes according to the circumstance. Static means it's the same all the time. Static means it's done before execution. A compiler does static work. It looks at the code and does something. Right? Dynamic work would be done real time in execution. Well, obviously it's too late to have the compiler be helping you during execution. The only friend you have during execution is the hardware itself. So yes, it takes transistors to build in that same intelligence for reordering that was built into the algorithm of the compiler. So you're spending space in the processor instead of time during compilation, but you get the advantage of dynamic reordering, and now you can be more likely to find data-independent n instructions in order to be able to do this. So what we're doing is hardware branch prediction, which costs more, but can be done. And the growth in the available transistors has allowed this to boom. And so you no longer find delayed branching to be very popular. This hardware branch prediction is relatively cheaper because the transistors have gotten so plentiful and there's so much area available on the chip. But anyway, let's continue, and at least with the idea of what would delayed branch look like. Look at this. If register 2 equals register 0, then take the branch. Okay, so that means that right here, right after that, there's nothing to do but drink tea. Okay, well, what we're going to do is try to fill that delay slot with useful work. In the first example, we're going to take something from before and put it here. Notice we're changing register 1, we're only reading register 2. So it's okay to have that action, which changes register 1, be done here. Because this then this is not different than this then this. So you'll see right here, we're going to take it from before the slot, before the branch, and put it in the slot. Over here, something similar is going to happen. In this case, if this is equal to 0, then we branch back to here. We had this, which is from the branch target. Okay, notice this is the branch target information. We're going to take the subtract and put it here. In other words, because what this says is if we take the branch, then do the subtract, this says take the branch, but before you actually get to take it, do the subtract. So the difference is, in this case, we do the add all the time. Putting it here would mean we'll do it all the time. In this case, we only do the subtract if we take the branch. We're going to be putting it here and therefore doing it all the time. Same thing here. We're going to, the fall through, or in this case you can see it's just a backward branch versus a forward branch, takes us to the subtract instruction. If I put it here, then it means not only do it when we take it, but do it all the time. So there's some conditions. The first one is the most desirable. The second two are, as I said, look what happens here. They each become, they each become moving this instruction into the delay slot. So here we go. If this, then take the branch, and by the way, do this also. This says, if this, take the branch, and by the way, do this also. This says, if true, take the branch, and by the way, do this also. So the subtract from the target moved in as it did here as well. And just a footnote is, A is obviously the best choice. It fills the delay slot with an independent instruction. In B and in C, the subtract instruction may need to be copied, increasing the instruction count. And in B and C, most importantly, this third point is, it must be okay to execute the subtract when the branch fails. Okay, in other words, when the branch doesn't go here, we're still doing the subtract anyway once you move it into here. It must be okay. In other words, that must not cause damage. If it causes damage, then it's not a safe instruction. Safe means it's okay to do it, even if we take the branch, even if we don't take the branch. Same thing here. So that's what scheduling delay branch slots looks like for one, and you can imagine that when it gets to be n, it's a very much bigger challenge. Now let's go to another approach called branch prediction. First we'll look at static prediction, then we'll look at dynamic prediction. Static is going to be done in advance, dynamic is going to be done real time. Okay, resolving the hazards by assuming that we're always going to take a given outcome and proceeding toward that without waiting to see what the actual branch outcome is. In other words, assuming I'll take the branch and go ahead and take it and continue executing, or assuming I won't take the branch and continue executing, and then find out later if the results of the comparison show it to be equal or not, show it to take the branch or not. In other words, choose a road and go even before you know if it's the right road. Okay, predicting. All right, that's the idea here. One thing to do is predict that you don't take the branch. Predict that you will not take the branch and just continue executing sequentially. Later, if you find out you took the branch, you obviously have to cancel and go down the right way, but you're always right, and there's no loss of cycles whenever your prediction is true. So let's just say that as the beginning. When we're talking about prediction, whether it's static or dynamic, if you made the right prediction, you don't drink any tea. You get useful work done. You only drink tea when your prediction was wrong. And that's a big improvement from always drink tea. Now we're down to drink tea only when your prediction is wrong. So what does that mean? If your prediction accuracy is high, you don't drink much tea, you do useful work instead. So if we get a prediction accuracy of 100%, no tea. Prediction accuracy of 50%, that means half the time drink tea for a cycle, half the time do useful work. What's the average value of lost time? Half a cycle now, not one full cycle. Got it? If your prediction accuracy is 90%, then you only drink tea 1 time out of 10, and you don't drink any tea 9 times out of 10, so your loss is only 1/10 of a cycle. Got it? The higher your prediction accuracy, the less wasted time in both cycles. So therefore, that raises the issue of, can we have high prediction accuracy? If so, how? What do we do to get high branch prediction accuracy? Okay, the first one we'll look at is predict that we don't take it. You always predict that branches will not be taken. You continue to fetch sequentially the next instruction, and when you find out you were wrong and we should have taken the branch, that's the only time you have to do a pipeline stall. That's the only time, right? So if you did take the branch, even though you predicted you shouldn't, then whoa, stop, flush the instructions after the branch, which would be earlier in the pipeline. If they're in the IF, ID, and EX stages, if the branch logic is in the MEM, you have 3 stalls. If the branch logic is EX, you have to flush out 2, and you have 2 stalls. If the branch logic is in the decode stage, like we have done in our hardware, then you only have to have 1 stall. So we'll have 1 stall when you're wrong, no stalls when you're right. So their average value is going to be something between 0 and 1 for stalls. You have to ensure, of course, that any instructions that you flushed out didn't change the machine state. What does it mean to change the machine state? What does it mean to change the machine state? Yeah, they didn't write anything into memory or registers. They didn't write anything into registers. As long as they didn't change any data, you can flush them out and nothing's wrong, okay? So we have to just assure that. And notice it says that in the MIPS pipeline, that comes automatically. You get that for free. The way the MIPS pipeline is designed, no writes will be done early. All writes are done late. Where do we change memory? In the 4th cycle of the pipeline. Where do we change register? In the 5th cycle of the pipeline. We do late writes. We don't do any early writes in the MIPS pipeline. So therefore, we're automatically safe from this. Won't cause us any problem at all. But other pipelines, deeper pipelines, CISC pipelines, may have a little trouble with this. Once you changed a register value, you'd have to go back and unchange it. Or you'd have to hold the change tentatively and not do it until you're sure that your prediction was right. Because if you flush an instruction but it's already made a change in the machine state, you haven't really flushed it unless you unchange the change that it made. Okay? And then you restart the pipe at the branch instruction destination that you should have gone to when you mispredicted. So we got it here. When you predict correctly, nothing's different. It's like it's not a branch. Dung, 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 off you go. When you mispredict, you have to flush. Depending on where you've located the branch logic, you may have 1, 2, or 3 stalls. We've located it here where there's 1 stall. And you have to be sure in any pipeline that you don't get bad consequences. And you have to be sure that you restart at the correct location. You made the wrong guess. Okay? So the consequences of a wrong guess are you have to fix your mess. But the consequences of a right guess are useful work instead of tea drinking. I mean, I'm not against tea drinking. Please don't misunderstand me. I love tea. I love to stop, spend time with friends, take a break. Tea's lovely. But when there's work to be done, you shouldn't be drinking tea. When you should be drinking tea, you should procrastinate and not do your work. But for processors, we don't want them drinking tea. We want them working. This is just a machine. It doesn't need to have human relations. It doesn't need to talk to its friends. So, all right, now, let's see what flushing looks like. Let's do a misprediction. All right, so the code goes, at location 4 is BEQ. At location 8 is, I can't even read it here, subtract. And so we say, okay, great, let's predict we don't take the branch. So fetch 4, then fetch 8, and then find out, oops, we should have taken the branch. In fact, these are equal. When these are equal, where are we supposed to go? Do we go to location 5? No. Where do we go? Why? The 5 means what? The 5 means 5-word locations, or 20 bytes, after this one or after this one? Yeah. PC plus 4 plus this multiplied by 4. This with 2 zeros on the end. Yeah, so we should go to 28. So what did we already do? We already fetched 8, and then we realized we have the wrong instruction. We should have fetched 28. So what do? We predict don't take, find out later we should take. So what's it time to do? We have to flush this, of course. We have to actually make all the control signals 0 for that so that it doesn't do any damage, or load in a 0 into the pipeline register so that it doesn't do any instruction at all. We have to make it into a no-op. We have to make it ineffective. And then we must make sure that here we did fetch from 28. All right? So this is a wrong fetch. It's the next one, but turned out to be wrong. If it had been okay, then after 8 would go what? 12 and then 16 and so on. If it was a correct prediction, but it turned out to not be because these were equal, so we're supposed to go to 28. So you can see what happens. Flush that, fetch 28, then fetch 32, etc. Does everybody understand the diagram? Are there any questions about what this means? Predict, and if you're wrong, fix it. You're seeing the fix it. We were wrong here. We predicted. Can you even see that the word flush has been written on top of the subtract? There was a sub here with 2 parameters and a result parameter, but that's wrong, so we flushed it. And you can see that where we need to go is 28. Any questions about understanding that? You're looking at it, but I don't know if you're getting it. I see a lot of faces that are not giving any sign of understanding or not understanding or anything. I have no clue if this is meaningful to you, so you have to let me know. Did you get what we're talking about here? Predict, and if you mispredicted, fix it. That's the summary of what we're doing. This is the fix it. You're looking at mispredict and fix. By now, I hope the word flush means something to you. I hope that diagram with the blue here after you fetch, but in the second stage realizing, no, not that, do this. I hope that's meaningful. Hope we know how to flush. Okay, to flush in the instruction fetch stage, we simply assert the flush signal, and what's it supposed to do? It's supposed to zero the instruction field of the IFID pipeline. So we just zeroed the instruction. So what is an instruction with 32 zeros in it? It's a no-op, isn't it? Actually, it's shift left logical, register 0, register 0, register 0, 0 bits, you know, whatever. But I mean, it's a no-op. Remember, we talked about it. If you have 32 zeros, it's a no-op. So yeah, we just put in a no-op, and the no-op means don't do anything, don't do anything, don't do anything, don't do anything. Drink tea. Enjoy your friends. Okay, now, let's continue. Predict not taken works really well for top of loop. Here's a loop top. We have top testing, and most of the time we should go in the loop and jump to the top, go in the loop, jump to the top. So most of the time we should be going in and not taking the branch. When do we go to out? When do we go to out? On the last iteration of the loop, right? So n minus 1 times we go in, and 1 time we go out. And you can see go in is sequentially continue, don't take the branch, and go out is take the branch. So therefore, for this kind of loop, predicting not taken is very good. You're n minus 1 times out of n, you're going to be right. 1 time out of n, you're going to be wrong. But you know what? I've already explained to you that top-tested loops are inefficient because they have an extra jump that's not needed. I hope everybody in their assembly language code by now realizes you should turn that into a bottom-tested loop, which doesn't have a jump. Does everybody see? There's 1 less instruction in this loop. What's the problem with bottom-tested loops? You take the branch every time except for the last, and then you don't take it. So predicting not taken is going to be wrong n minus 1 times out of n, and only correct on the final time, only correct 1 time out of n. So it's the wrong way to predict. Bottom-tested loops doesn't work well to predict not taken. What should we predict for them? Predict taken, yeah, predict always taken. Then you'll be correct n minus 1 times out of the total n, and you'll only be wrong on the last one. Can everybody see here that in either case, the best you can do is be right every time except the last? Because the last goes somewhere else that the other ones didn't go. So even if you're right on all n minus 1, the last one, you're going to be wrong. So that's the best you can do. If you execute a loop 1,000 times, you can only be right 999. If you execute a loop 10 times, you can only be right 9. Nobody has a crystal ball to say, take it, take it, take it. Oh, this time I think we shouldn't take it. You know, there's no way to understand when you're at the last iteration on a loop. Tamam, okay? So that should be clear here. So for this kind of structure, we need a predict taken approach. Okay? So predict taken is predicting that they always will be taken. That would be great for bottom-tested loops. But the problem with predict taken is, where do I go to? And the answer is, I need to calculate that from the, remember, the 16-bit immediate field of the instruction with some other stuff. It's a calculation. I can't know it directly. Whereas predict not taken, I can take PC and add 4 and I know the address. But for the other one, I need to get the instruction and decode it in order to know where I would go next if I was to take it. So the trouble is now you always have 1 stall cycle, even if the branch detection has been moved to the decode stage. The question is there a way to calculate that branch target address and then cache it so you don't have to calculate it every time? Think about that. The first time I come to that branch, I figure out the destination address of taking it, I cache that, and now every time I'm predicting take it, I just use the cache value. I don't have to do any calculation. Then I could get it down to no stall or no flush, n minus 1 times, only a stall on the nth time, the final time. But I have to have the address and have it in a little cache. Okay? All right, as the branch penalty increases when you get deeper pipelines, read the last thing here. Simple prediction schemes like we're talking about, which are called static, always go a certain way, will hurt performance. What we need is dynamic branch prediction, which with hardware support understands during program execution the behavior of our branches. During execution, understands how they're behaving and makes a dynamic branch prediction real time using transistors that do calculations in the hardware. Wow. You mean we're talking about an algorithm buried inside the processor which watches what our branches are doing and makes best guesses? Yes, that's what we're talking about. A history table and a little algorithm that's going to take that state and interpret as what the next best prediction should be. So we're going to need runtime information, and that can never be given by the compiler, and it can never be done statically. It has to be done real time in the machine. So that's what we talked about earlier. We mentioned that, yes, it's expensive, but my friends, we've got not millions, not tens of millions, not hundreds of millions. We're now literally in the billions of transistors as our budget. So what's a few tens of millions of transistors to do this? No big deal. We've got it. Wouldn't have said that 10 years ago. Certainly wouldn't have said that 15 or 20 years ago. So now we're talking about dynamic branch prediction with hardware support. Okay, that's where we've come to now. Simple schemes give us the idea. You can get it right much of the time, but it depends on the loop. And what about if it's an if-else? And yeah, there's just a lot of things that we didn't cover here. But the best would be to know the history. What have we been doing? And do the same next time. Or better yet, use extra information to make an even better prediction. We don't have a crystal ball, but we could use all the information of our real-time execution, including data values, to help us know what we should do. What we're going to need is a branch prediction buffer, sometimes known as a branch history table, in the instruction fetch stage. Fetch? Yeah, the first stage. We're going to put some new hardware in the very first stage, not just the instruction memory. We're going to actually put some history of our branching as a table. A table? You mean like a data structure table? Yeah, like a table. Only it's a hardware table. You mean extra memory holds you? Yeah, but it's not called memory because it's not general. It only holds one thing. It holds history of where we've branched for that particular branch instruction. Of course, there's many branch instructions, so each one will have to have a history with some bits. And you mean we're going to be managing it? Yeah, like a little mini database? All in transistors? Okay? You got it? So we're taking lots of the Kavram law of computer science and we're putting them right in transistors, in structures that run algorithms with data structures right in the instruction fetch stage. Wow, I didn't know we could do that. Oh, sure. You can do it if you've got the budget. If you've got the transistors, why not? Algorithms in hardware are easily doable, but you just need to have the transistors and the will to do it. Anyway, what we're going to do is we're going to address this buffer with the lower bits of the PC, and it's going to contain bits that are passed to the ID stage through the pipeline register. It's going to tell whether the branch was taken last time or not that we executed it. Now, this branch history table helps our prediction accuracy. Is it always perfect? No. We still might mispredict. When we mispredict, we're still going to have to flush, like we talked about. It might be a wrong prediction for this branch, or because it's just the lower bits, it might be from a different branch that has the same lower PC bits. But that doesn't affect the correctness of it. It just affects the performance. We'll have some drinking of tea while we flush the pipeline on the misses. The branch decision still needs to occur in the ID stage. So we predict in IF. We find out in ID if we did it right or wrong. Okay, we predict in IF using this help, as opposed to predict always the same, I go this way all the time. But we find out in the decode stage if we predicted right or wrong. Okay, and if the prediction is wrong, then what we're going to do is flush the incorrect instruction from the pipeline, restart the pipeline with the right instruction, and watch this. We're going to smarten up. We're going to learn from our mistakes. The prediction bit or bits are going to be changed. We're going to say, you know what? I predicted take it, but it turned out to be not take it. Let me get smart. Next time I'll predict not take it. So if we're running a loop and I'm guessing wrong, it fixes and starts guessing right. And so if you run a loop 1,000 times, 10,000 times, 50 times, whatever your loop iteration count is, and they don't all just go up to 10 like in student problems, I assure you there's loops that run many, many, many times in real life problems, you'll start guessing right. You won't guess wrong all the time and be dumb. Look at this. Look at this. A 4096-bit branch history table, when run with programs from the spec integer suite, including NASA 7, no, sorry, these are floating point, NASA 7 and Tomcat V, and EQN tot, which I forget what it is, misses, that is mispredicts, somewhere between 1%, wow, that's pretty good, 99% correct prediction frequency, up to 18%. That's not too bad, 82% correct prediction frequency. So this is not like flipping a coin, algebra, you know, am I right or wrong? This is high accuracy branch prediction. 99% accuracy prediction for some programs. Fairly serious programs, the kind that you test performance with. Worst is 82%. Okay, now is 4,096 bits a lot of history to store? Not really, not for modern processors. That's not a serious amount of transistor budget. It's a little bitty mini memory that'll tell us what we did last time, and if we did it wrong, we change our prediction. Okay, that's the idea behind it. It dynamically can change our branch prediction. Now, the branch history table tells me if I should take it or not, but it doesn't tell me where to go to. We also need to have a second thing called the branch target buffer. And so look at this. The instruction memory gives us the instruction, or 0 if we're flushing, or now I've got a third candidate, the branch target. What would that give us? What would the branch target buffer give us? Obviously a stored instruction, right? Because that's what this gives us, a stored instruction. That's what this gives us if I want to put a no-op. So if you want to put an instruction here, it's got to come through this multiplexer. We know what this is. Give the address, and what you fetched at that address goes here. This says put a 0 in. It's a no-op. So what's this putting in? An instruction. What instruction? Oh, the instruction stored at the branch target destination address. Yes, this will be the one that you want to go to. The branch history table will tell you if you go to it, and the branch target buffer will tell you where you go to. Now, the thing found at where you go to. Aha. So that's the two parts needed. When you're branching, you need to know, do I go there? And you need to know, where do I go? Okay? So we've prefetched the instruction, or instructions, they're already here. In other words, from this full memory, we pulled out the branch instructions, and we put them all here. So if the next one you're going to go to is a branch instruction, my friend, it's already ready here for you, and the predictor will tell you, take it or don't take it. Don't take it means pull this one out. Take it means pull this one out. Okay? Okay, so now we've got our solution here. The branch target buffer can cache the branch taken instruction while the instruction memory is fetching the next sequential instruction. If the prediction is correct, stalls can be avoided no matter which direction they go. With static predict always taken, you can't avoid stalls sometimes. With static predict don't take, you can't avoid stalls sometimes. But read that last sentence. That is the gold mine that's available here for dynamic prediction. If the prediction is correct, stalls can be totally avoided no matter which direction, take it or don't take it, we're going. Totally avoiding stalls. But there's an if. If the prediction is correct. How correct is the prediction? Well, 99%, 82%, in that range. Pretty good stuff. Pretty good stuff. I hope I'm convincing you. Let's spend some transistors. This is a place to gain some performance. We're not just talking theoretical algebra. This is really done in most machines. Do you remember what it said about 10 slides back? It said, delayed branching works great if the pipelines are short. But modern processors are moving to this because the transistors are available. Yes, it's complicated. Yes, it's expensive. But this is the way to go to squeeze out the performance from the control hazards that we have to live with. Squeeze out the performance. Now, MIPS helps us with a short, simple pipeline, but not all processors have short, simple pipelines. You can be sure that Pentium and AMD and dual core and all that stuff, those are very complicated, long depth pipelines because they're CISC in their origin. Okay, now, are there any questions about what we've said so far? That's what I'd like to ask. Any questions about what we've said so far? Principles and some practice. Now we're going to go a little bit deeper. But before we go into more detail, I want to make sure that you're still with me here on this idea about branch prediction dynamically, using a branch history table and a branch prediction buffer. Does anybody have any questions? Anybody want to understand, clarify? Let me know that you're not following 100% and you'd like to. Yeah?
What is the percentage of branch instructions on average program?
Yeah, I can give you some rough numbers. In the spec suite, which as you remember is a representative set of reasonable integer programs and reasonable floating point programs, branching typically will run 15, 18, 20%, okay? In RISC machines, 15, 18, 20%. Obviously, all those programs are actually high-level language programs compiled into whatever the target architecture is. When the ISA is a simple RISC like MIPS, it tends to be 15, 18, 20% branches, okay? So it comes up pretty frequently. So 1 out of 5 instructions, let's say, or 1 out of 6 is a branch. And if you always have a 1-cycle stall, that's going to add 16%. And your ideal CPI is now 1.16. If you can cut it down to 1% of that, it's going to be 1.016. All right? If you had a 99% accuracy in branch prediction, et cetera, et cetera. Okay, let's talk about branch prediction if it's a 1-bit memory. All right? It either says take it or don't take it, and it records the value you had last time. Okay? With a 1-bit predictor, you're going to be incorrect twice in a loop. The first execution is going to be wrong. You'll then change it. All the other iterations will be wrong until the last one when you do the opposite thing. I hope we're all convinced that in a loop you do the same thing n-1 times, and then on the nth and final time you do it differently once. We all agree that's how loops work. Da-da-da-da-da-da, chick, or chick, 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 devamet, right? It depends if it's a top-tested or bottom-tested loop. So you're going to do n-1 things the same, and the last one different. If you have a 1-bit predictor, what happens when you do it n-1 times the same and then it goes different at the end? Your prediction's wrong, and you say, oh, change it. So what are you going to predict? The next time you come to that loop, you're going to predict, don't take it, do the thing I did at the end. But of course, the first thing you do is the same as all the other n-1 things you do. The last one's different. So changing it when you're wrong on the final iteration just means you're also going to be wrong the next time you come back to that loop, right? And we re-enter loops many times. Nested loops are very common. And called routines that have loops in them are very common. So you're going to miss on the first because you changed it as you were leaving, and now it predicts the leave, but you don't leave. And you're going to miss on the last. You'll miss 2 times out of a loop. So n-2 will be correct, and 2 will be wrong with a 1-bit predictor. That's pretty clear. And this just justifies that. So for 10 times through the loop, you would have an 80% prediction accuracy. What's the maximum accuracy you could have in a loop that runs 10 times? The best you could ever have? 90. We'd love 100, but we cannot. We already agreed. n-1 correct predictions and 1 wrong prediction is the ideal. That's the best you're going to be able to do. So with 90% as our standard, we're hitting 80 with a 1-bit predictor. Well, is there any way to get a little more performance out of that? I think there is. How about we go with a 2-bit predictor? Here's a little state machine. I'd like everyone to use your knowledge of CS-224. Look at this state machine and figure out what happens. If we predict that it'll be taken, and it's not taken, we still predict that it'll be taken. In other words, 1 wrong doesn't cause us to move from predict taken to predict not taken. 2 wrongs cause us. Watch, if I get it not taken, and I'm predicting taken, and I still not take, then I predict not taken. You have to be wrong twice in order to change your prediction. Okay? Is that okay with everybody? That's what this state machine shows. And if you're predicting not taken and it's taken, you still predict not taken until it's taken a second time. So it takes 2 wrongs in a row to get you to change your prediction. Okay, now, take the loop, take the loop, take the loop, take the loop. We all agree that after a while your predictor is going to line up with what's happening. And now finally it's the time to check. It's your last iteration of the loop. What's going to happen? You were wrong. So that means you're going to move from here over to here. But you don't change your prediction. So now when it comes top of the loop again, time to re-enter that loop and run it another time, you've got the right prediction. You predict that it's taken. When it's taken, you just move back to over here. You don't get 2 wrongs in a row because a loop only exits once. So when you re-enter the loop, your prediction is still what it should be. Everybody understand that? So with a 2-bit predictor, yes, you doubled the number of bits in the prediction algorithm, but we said transistors are cheap. What you get is you squeezed it up from 80 to 90% accuracy if you run 10 times in the loop. Okay? Or another way to say it is you move from 2 wrongs to only 1 wrong prediction. You get it down to the minimum. Okay? And then finally, where do I start in this? The branch history table stores the initial state of this finite state machine. This is called a finite state machine or a state machine, and it needs to know what's my initial state. Do I start here? Do I start here? Do I start here? Do I start here? Well, I think you can probably see that it's either going to be start here or start here, because these are the stable ones. With 1 mistake, you don't leave it. And if after 1 mistake you get it right, you come back. These are the stable ones, so I'll either pick that or I'll pick that. Where would I get that information? Predict taken, predict not taken. Where would that come from? The initial state, the starting state. In other words, if I'm going to have a state machine, I got to know, do I begin here or do I begin here? And it says that's stored, but who put it in there? How is it known? Well, control unit could write it in there, sure, based on what?
If you don't take the
yeah.
predict, if you don't take the branch, so only we have program counter.
Yeah, tamam, but first time when the machine is powering up, we're about to run a program, we need to initialize this and say I start there or I start there. Maybe with a little compiler help. This is a top tested loop. This is a bottom tested loop. The compiler knows how it placed the branching. It knows if it placed it at the bottom or the top of a loop. Or it's no loop at all. Oh, no loop at all. Well, then what? Yeah, we're only going to come through it once unless we keep coming back into it. But you know, if-elses can be repeatedly called as well. And cases can be repeatedly called as well. They're going to have a bunch of branches in them. So it still makes sense to have this history table. But we need to initialize it correctly. Okay, that's all we're going to do. We've gotten now pretty sophisticated. I haven't gone deep into the hardware, but you've got the idea about the level of algorithms that are taking place now in hardware in modern processors, okay, for dealing with the control hazards. We also dealt with the data hazards. We also briefly touched on structural hazards and pointed out that a simple pipeline like MIPS doesn't have any, but complicated pipelines would. All right, now I'm going to move to a new topic called exceptions. Okay, exceptions are sometimes called interrupts. Raise your hand if you've heard the word interrupt. Yeah, your mother and father said, don't interrupt me when I'm talking, didn't they? Lafa me kesme. Okay, this is, interrupting here is ishleme me kesme, you might say. Or don't cut off the processing. An interrupt actually changes the order of execution, but the program didn't say branch or jump. It changes, the next instruction to be fetched won't be the sequential one, it'll be something different because of what? Exception, istisna, and what else can we say? Interrupt, kesmek, okay, imdat, you know, some kind of an unusual condition that's going to cause the program to change. What kind of conditions could there be? Well, here's one. We have an R-type instruction, and the ALU says we had an overflow. Do not trust that result. Something happened here, and we've got an overflow. That number I just gave you, it's not a good number. I'm telling you, warning you, overflow occurred. Yeah, you need to know that. You don't want to take that number and launch your missile or have your airbags or your automatic braking be based upon a bad calculated number, do you? Or you try to execute an instruction, but it's undefined. You get into the decode stage, and you're looking at the opcode. What is this bit pattern? I don't know what this is supposed to be. Something went wrong, and you fetched an instruction that's undecodable or unexecutable. You got a problem, don't you? And you just found it out right in the middle of the pipeline of executing these. Or an I/O device requests service. And so because the I/O device is saying, hey, I need the operating system to please run some code, guess what? You have to stop. We're moving you off. And the I/O device is going to run operating system code, and the disk is going to spin, or the printer is going to print, or the keyboard is going to get read, or the mouse is going to get read, and new input's going to come in, and then we'll put you back later. So you stop. So the normal execution of the program is stopped because of an external reason called an I/O interrupt. Or the operating system requests some kind of service. The operating system needs to run some kind of routine. There's a page fault, or a translation look-aside buffer exception, or whatever. Or the hardware malfunctions. Some such reason which stops the normal flow of execution. And your next instruction is not going to get fetched, either because you caused the problem or there's an external problem or circumstance. Tamam. That's the definition of an exception or an interrupt. Okay? So what has to happen here is the pipeline needs to stop executing your code. The offending instruction, for example, in the first two, there's an instruction that caused that. There may be one here that caused this. When you go to memory and you say, oh, I want this particular location in memory, it could be you caused the page fault. You're asking for something that's not in memory. It's on disk. We have to stop and spin the disk and bring it in. So therefore, could be you caused these. Could be it was externally caused. Whatever. But we need to therefore stop executing the offending instruction. Let all the prior instructions in the pipeline go ahead and finish. We need to flush out all the following instructions, get rid of those, And then we need to set a register to show the cause of the exception. Was it this, was it this, was it this, was it this, was it this? And then we need to save the address of the offending instruction. In other words, which instruction's address, because we're going to go fetch it again maybe and try to fix it, or at least tell the user this was the RMA's, he did it, you know. And then we need to jump to a prearranged place in the operating system, which is the kutarma. Let's call akut. We had an earthquake, the building fell down, get the dogs, get the rescuers. You know, suddenly normal things stop. We need to bring in the kutarma operation, okay? So the operating system now runs code to handle the exception. Not your program, which caused it, but a different program in the operating system which says, okay, we're the big boys, look out, everybody move away, cordon off, keep the public out, the police have come, or the MNED, or whoever. We're going to take over this site here. We're going to run our code, and after we clean up the mess, then you guys, you civilians, can have it back. And think like that, okay? Your program is civilian, and operating system is the military police, or the army, or AKUT, or somebody like that. So then we're going to jump to a prearranged address, which is the address of the exception handler code. You know, the code to handle haletmek, to handle the exception. We're going to go somewhere else. After this, 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 we're going to go somewhere else. Okay, the software, or the operating system, is going to contain these exception handlers, and when it runs, it's going to look at the cause of the exception, which you stored here, you showed that in a register, and it's going to try to deal with it, right? Fix it if it can, or put a blue screen of death up, or whatever. There's two kinds of exceptions, the kind that are caused external to your program and the kind that come internally from your program. The external events are called asynchronous exceptions, and they often are called interrupts because they're asynchronous. They happen between instructions. So we can let the instructions that are currently active in the pipeline complete before we pass control over to the operating system for handling the interrupt. And you simply suspend the user program, handle it, and then resume. Because the user program didn't cause it, it was caused externally. Okay? The other kind are called traps, or exceptions. And these are synchronous to the program execution, and they happened inside the program. They're caused, in fact, by internal events. So the condition that caused them has got to be remedied or at least analyzed and understood by the trap handler for that particular instruction. There's one instruction that's the cause instruction. It's coming internally, see? So we've got to look at that instruction. That's why we need to record its address, or in save the address of the offending instruction. You know what to offend is? You know, kabomak, or, you know, something like that. So the offending instruction. We need to save that. So that means we're now going to go in here and analyze it. We're going to stop the offending instruction midstream. In other words, if you cause an overflow in the ALU, your execute stage is the last stage you're ever going to see. We're not going to continue. Right then and there when you overflowed, or right then and there when we decoded and found an invalid opcode, you got to stop. We're freezing. The ones ahead of you finish, the ones behind you, too bad for them. You are put in prison, right? You're going to be jeza, all right? The offending instruction may be retried. It's possible that we'll try to restart it again, or maybe simulated in software by the operating system. Or don't run the real instruction, but simulate it in a bunch of code that does in software what that would do in hardware. There's ways to do that. And the program may continue, or maybe we just kill it. It's possible to abort the program because of the exception that was caused. So that's what happens. Exceptions are something that are not planned on by your program. They're not part of your logic. You didn't write them in high-level language and compile them, but they happen. They happen for two reasons. Internal, called traps or exceptions, and external, caused interrupts. Two different categories, both of which we handle, but in a slightly different way. Did you get the slightly different way? This says, okay, it's not caused by any of our instructions, so we just pick a place and we say, you guys finish, we're jumping in now. Nothing wrong with you, you just have to wait because we're the outside guys to come in and fix the problem. This says, there's one of you that did it, and you finish and you stop and we caught you and you're going to go to jail and we're going to analyze and figure out and see if we can save the situation. If we can, we'll restart and retry you again. Don't do it again though. So there's one cause instruction in the case of traps. In the case of interrupts, nobody caused it, it happened outside. Okay? The printer needs paper, or the disk you know, has a page ready, or the power supply says, hey, we're failing, it's time to go down, whatever. Something like that. So external versus internal. All right, we'll take a break, and after break we'll come back and we'll continue a little bit more on exceptions. So take 10 and get some oxygen and go downstairs and get a coffee, and then come back in 10 minutes and we'll continue with exceptions.